Greetings everyone, welcome back into trigonometry. Time to talk about some of the more advanced trigonometric identities that are used not just in trigonometry but in all of the other maths that come after that also dip into trigonometry. For example, calculus uses several of these identities on just about every little thing that it uses in mixture with trigonometry. I'm going to apologize beforehand for the length of this video. I haven't finished shooting it yet, as you can see, but I'm going to guess that it's going to be lengthier than the other ones. And that's just because all of these identities really are the same concept, and the examples are very repetitive. Like it's the same idea, using the identity to figure out some angles, using the identity to figure out some trig ratios, things like that. So I'm cramming them all together in this one video so that they're all in one place. Okay, so the first round, the first set of identities that come up that sort of spurn the rest of them are the sum and difference identities. Okay, if you're looking for a full-blown proof on these, I suggest you go into the OpenStax textbook. They have a really nice, concise way of showing you why these particular ones are true, starting with the sines and the cosines, and then everything sort of just builds from there. Okay, so here's the idea though with these. In trigonometry, I don't have all of those nice, pretty principles like you do with a lot of other algebraic structures, like distributive property, for example. A lot of people like to have that distributive property so that they can break up large groups of things. You know, it works out really well in solving equations for getting rid of parenthetical objects. However, the sine of a plus b is not equal to the sine of a plus the sine of b. In fact, the higher you go in all of our more advanced operations, it's very seldom that you run into something that's quite like that, right? Like logarithms. Log of a plus b is not the same thing as the log of a plus the log of b. Several things are, it's sort of outside of the realm there, but trigonometry is one of the worst. Trigonometry does not play well with other branches of math, sort of has its own way. And this is a main example right here. I don't have a distributive property for a trig function. However, I do still have a way to break these down if I need to. So if I want to do the sine of two angles that have been added, okay, then I can do the sine of the first one, the cosine of the second one multiplied, plus vice versa, cosine of the first one, sine of the second one multiplied, and so on and so on. Okay, so it always starts out with proving the sine and the cosine of something, and then doing the sine over the cosine and simplifying then gives you a version of the tangent as well. So these are our basic 6 beginning identities here. And then all of the rest of the identities that in this section build off of these. Okay, so here's one big use right away that come out of these. I have a limited few memorized trig angle and their ratios. 30, 45, 60 to be example, right? We know the sine, cosine, and tangent of 30 degrees. Those are ones that we've been made to memorize because 30 degrees happens a lot and because it comes from a nice, easy shape. Any angles outside of those, typically we don't have a nice, exact value closed form for their sine, cosine, tangent ratios. Well, this is sort of an expansion now. You can start to build more angles that you know the exact form of, okay? And that's the trick here. I could just plug sine of pi over 12 in if I'm looking for a quick decimal answer. The goal here is not to get the decimal answer. The goal here is to have an exact form, something that I didn't have to truncate, something that I can put in for simple symbols, like maybe a plus, a minus, maybe a square root of something here or there. Kind of like the cosine of 30 is square root of 3 over 2, right? Something simple-ish like that. So let's build here. Sine of pi over 12, okay, incidentally, pi over 12 is 15 degrees, right? Half of 30. So half of pi over 6. The way I'm going to do this is I'm going to find the sine of pi over 3 minus pi over 4. Okay? Incidentally, in degrees, that's going to be 60 degrees minus 45 degrees. Right? And you can even see it from the common denominator here. 3 and 4, common denominator is 12. That would give me 4/12 minus 3/12, which is 1/12. So I'm going to be doing the sine of pi over 3 minus pi over 4. Now that I've rewritten pi over 12 into a structure that fits one of my systems here, okay, then I can pick one of these formulas. Right here, sine of A minus B. I can do sine of A cosine of B minus cosine A sine B. So that's what I'm going to do right here. That's going to be sine pi over 3 cosine pi over 4 minus cosine pi over 3 times the sine of pi over 4. All right, and then from here, those are the ones that we do have memorized. I specifically picked the 60 and the 45 because those are two of the angles that we do know the closed form of, right? I have the sine of pi over 3, the sine of 60 degrees. That's your square root of 3 over 2. Cosine of pi over 4, that's square root of 2 over 2. Minus cosine of pi over 3, that's 1/2. And sine of pi over 4, that's square root of 2 over 2. And notice what we get is something that already has a common denominator between two subtracted fractions. What I get is something that's entirely over 4, right? 2 times 2, I'll get a 4 here, and 2 times 2, I'll have a 4 denominator here. They'll have a common denominator, I can add them together. Square root of 3 times the square root of 2 is the square root of 6 minus 1 times the square root of 2 is the square root of 2. So this is what I'm looking for right here. A concise, closed form, exact value of the answer to what is the sine of pi over 12 radians, the sine of 15 degrees. Is going to be the square root of 6 minus the square root of 2, all divided by 4. Okay? So if you're in doubt a little bit, then we'll have to plug it into your calculator here, just to double check. I'm going to switch to radians. Sine pi over 12. Sine of pi over 12 is 0.25881, blah, 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 blah. Right? Also, if I do square root of 6 minus square root of 2 divided by 4, same thing, 0.25881, blah, 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 blah. Okay? So, next, cosine of 75. Okay? So for that one, let's do the cosine of 30 degrees plus 45 degrees. Again, the goal here is to rewrite what I'm doing as a structure that I have an identity for. Okay? So now that I have this structure, I'm going to pick the identity that I want, the cosine of A plus B. So that's going to be equal to cosine of A, so that's 30 degrees, cosine of B, that's 45 degrees, minus sine of 30 degrees times the sine of 45 degrees. Okay, so the cosine of 30 degrees is square root of 3 over 2. Cosine of 45, square root of 2 over 2, minus sine of 30 is 1/2 sine of 45 square root of 2 over 2. Notice anything familiar? The answer here happens to be the same. And that's just a coincidence of the way I picked the problems, sort of. I don't mean that, what I mean is that we're not going to get that same thing every time, okay? However, there is something to notice here, okay? The thing that you should notice is the 15 degrees plus 75 degrees is 90 degrees. In other words, they're complementary. And these are cofunctions, right? Complementary angles of cofunctions are always equal. That's why the sine of 30 and the cosine of 60 and vice versa are equal like that, right? We've seen that before. We've talked about that already. So that's why these two are coming out to be equal, and it's just happenstance that I picked those two particular angles, okay? But the idea is the same. Okay, I can split it up into different angles and then pick whatever one of these that I need to set up. And it doesn't have to be acute angles. I can do the same thing with any angle as long as I can find two constituent angles that I can quickly and easily get the sine, cosine, and tangent of, right? So in this case, tangent of 165. That's going to be 165 is 180 minus 15. That's not going to work because the tangent of 15 is going to be more advanced than I'd like to deal with. 165 could be 135 plus 30. Okay, so let me see. Let me do this in purple. This would be the tangent of 135 plus 30. That's one way to go. I could also do 120 plus 45. All of these are angles that are within my memorized knowledge. 135 is a quadrant 2 angle that has a 45 degree reference angle. So I can use all my 45 degree knowledge for this angle here, just in quadrant 2. And then, of course, there's 30 degrees. Okay, so I use tangent of A plus B. So I'll be using this identity, which is going to give me tangent of 135 degrees plus tangent of 30 degrees divided by 1 minus tangent of 135 degrees times tangent of 30 degrees. Okay, so where does that land me? Tangent of 135 is the same as tangent of 45 degrees, except in quadrant 2, tangent is negative. So that's -1. Plus tangent of 30 is square root of 3 over 3. Right? Now, in the bottom, I have 1 minus, and it's the same two calculations, just multiplied. So that's -1 times square root of 3 over 3, like so. The only thing that's going to happen in the first step here is I'm going to get a plus instead of a minus with this double negative. And I'd like to not have fractions inside of a big fraction. So first thing I'm going to do is I'm going to multiply everything by 3. So times 3, times 3, times 3, times 3. All right. So then in my next step here, what I have is -3 plus the square root of 3 over 1, oh, I'm sorry, not 1. 3 times 1 is still 3. Last time I checked, 3 plus square root of 3. Okay, so those aren't exactly the same thing, are they? Not quite, right? Because of the negative on the 3 there. That'd have been nice, though, if they would have wiped out. Okay, so then the only other thing I can do now to fix this is to multiply by the conjugate of the denominator. So I will be multiplying here by 3 minus the square root of 3, like so. And that means I'm going to have to do the same thing in the numerator. 3 minus the square root of 3. So then this is going to be equal to negative 9 plus 3 square root of 3. Again, same thing, plus 3 square root of 3. And then positive times negative is minus. Square root of 3 times square root of 3 is 3. In the denominator, I have a conjugate, so the two inside terms are going to add out to 0. Right? That's the whole point of doing the conjugate. And then I've still got a minus 3 here. Okay, we're almost there. In the top, negative 9 minus 3 gives me negative 12. And I have plus 6 square root of 3 over 9 minus 3 is 6. And since I can divide 6 evenly into both of those, I'm going to go ahead and do that. That's going to give me negative 2 plus the square root of 3. Okay? So, the tangent of 165 degrees is equal to negative 2 plus the square root of 3. Right? So not a terribly bad final answer to write up there. I know it was a few steps to get there, and tangents tend to be a few more steps than the other two in these formulas. But again, the idea is not about finding a quick answer. Okay, so don't let the steps throw you off here. The idea is to have a closed form, an exact answer, something that's not a decimal that I had to chop off. Okay, that's the main goal of this version of those problems. That's one of the things that these are used for. Okay, the next example in the next scene will show you the flip side, something else that we use these for. Go ahead. The next purpose or purposes that these identities are used for quite often is to either split up or bring together, simplify expressions that have trigonometry in them. Sometimes just to even make something, I said simplify already, but it altogether just look simpler. To sometimes look at interactions that we normally would not have been able to do. Also, we can talk about trig ratios of angles that we don't know the angle measurement, but we know some of the trig ratios. Sometimes we can use these to mix together. So that's the three examples I have here. I can create an identity for something. I can simplify or make an expression a lot easier to look at. Or I could talk about angles that I don't know the angle measure, but I can figure out trig ratios for and how to intermix those. Okay, so let's look at these right here. The tangent of a plus pi, where a is any angle. The idea here is to construct some identity of something that's useful here. Tangent has this special ability to always be the same when you go a half of a circle away from a certain angle. Okay, so this is actually a very useful identity that we'll be talking about here. Tangent of a plus pi would be equal to tangent, I'll use the a plus b form here. So that's going to be tangent of a plus tangent of pi over 1 minus tangent of a times tangent of pi. Okay, but what's the tangent of pi radians? Right, tangent of 180 degrees is 0. So in other words, this piece right here is going to go to 0, and this piece right here is going to be 0 also. In the numerator then, I have tangent of a plus 0, which is just going to be tangent of a. In the denominator, I'll have 1 minus, now look, this is 0 times, it doesn't matter what this is, 0 times that is going to be 0. I have 1 minus 0, which is just 1. Okay? So in other words, what we've just shown is that the tangent of any angle plus pi radians is equal to itself. That's an interesting property of tangent. Okay, next example. What if I have a sine that I need to have a mixture of two different angles, but I'm getting those other two angles from some inverse trigonometry? So in other words, I've found some value, x is some ratio. I'm going to be doing the inverse cosine of that ratio. That's going to give me an angle. I'm going to take whatever x is and double it as a ratio and do the inverse tangent of that, and that's going to give me a different angle. And then the subtraction of those two angles gives me another angle, which I will then be doing the sine of. Okay, so that's a lot of trigonometry going on in there, and I would like to know if there's a way to simplify this into just some algebra, right? Something that I can intermix with the rest of maybe some other problem or some other piece of the world. Okay, so let's start by drawing these things out. If I have some angle, and I don't even really care what that angle is, okay, I'll call it theta. An angle theta has a cosine of x. In other words, this would be x and this would be 1, right? And then let's say there's some other angle like this, okay? So a completely separate picture here. There's some other angle where when I set it up, I'll use gamma here. So that when I set this up, the tangent is 2x. Okay, so in my triangle here, that means that my opposite side is 2x and my adjacent is 1. Right? Okay, so to fill this out, let's go ahead and use Pythagorean theorem right here. This is going to be 1 squared minus x squared and then square rooted. Okay, so this the opposite side over here, that side right there, is going to be the square root of 1 minus x squared. And on this guy right here, I'll do 1 squared plus 2x squared, which is going to be 1 plus 4x squared, and then square root. And that's going to give me my hypotenuse here. 1 plus 4x squared would be my hypotenuse. Okay? But regardless, what's happened is, since I want to do this, it has become the sine of gamma, which is this angle, minus theta. Like so. Which I can then employ this. Well, I could have done that before anyway, right? I could have done that before anyway. But you see the pattern here. This will be quicker to write with just the symbols. So that's going to be sine of gamma cosine of theta minus cosine of gamma sine of theta, right? Okay, now here's the thing though. We already know the cosine of theta, okay? Because that's where this came from. The cosine of theta, that piece right there, is just going to be x. Okay, so this one's x. The sine of gamma here, sine is opposite over hypotenuse. So that's going to be 2x over the square root of 1 plus 4x squared. Okay, so I'm multiplying those two pieces minus the cosine of gamma, which is this one, So that's going to be 1 over the square root of 1 plus 4x squared times the sine of theta here, which is going to be the opposite over the hypotenuse. That's just square root of 1 minus x squared. Okay, so let's simplify this a little bit. Notice both of these are going to have the same denominator because it's just that square root times 1 and that square root times 1 for both of my denominators here. This is over 1, this is over 1, right? So what I'm going to get right here is 2x squared minus the square root of 1 minus x squared. And then that's all over the square root of 1 plus 4x squared. And that's how I would leave this particular answer, okay? It may not seem like we've made this a lot nicer, but we actually have, because we've been able to take it out of the trigonometry world and bring it back into the world with the rest of maybe some other algebra that I'm doing in the rest of the problem, okay? Now remember, these aren't necessarily part of the rest of the problem that I'm doing. These are visualizations that are helping me understand the sine, cosine, and tangent ratio values that go into the situation, okay? The rest of it is just the structure of this, okay? But the important point is I was able to simplify out of a complicated trigonometric relationship here into something algebraic. Even though it looks messy algebraic, we do actually consider this a bit more simplified than that, because it's very difficult to do anything with these particular things. Okay, next we have the situation where I don't know what angle U or angle W are. And yeah, I know we could do some inverse trig, like I could do the inverse tangent here, I could do the inverse cosine here, and we could actually solve for those angles, sure. But there's going to be a lot of loss of accuracy there for one, okay? Plus, we really want you to, practice these particular identities and talk about how they can form other relationships here, okay? So the tangent ratio of U is negative 5 over 12, and it tells us that U is in quadrant 2. So that means U looks something like this, and it means that I can set up his ratio like this. This would be negative 12. I'm sorry, not negative 12. This would be negative 5. Oh no, I was right before. Never mind. I'm losing my mind. This is negative 12 because it's in that direction, and then 5 is over here, right? Because tangent's opposite over adjacent. Okay. Then I can also solve for the hypotenuse there. 5 squared plus 12 squared, 25 plus 144 is 169. Square root of that is 13. So 13 happens to be the hypotenuse over there. And then same thing, same idea for cosine of W here is 7/8, and W is in quadrant 4, right? Remember, cosine is positive in quadrant 4. So if I were to set up the angle for W here, the triangle for W, then the cosine is 7/8. That means the adjacent here is 7 for the x-axis, and 8 is the hypotenuse. So then I want to find the other side over there. I'm going to end up doing 8 squared is equal to 7 squared plus whatever my other opposite side, I'll call it h squared is. So that's 64 minus 49 is equal to h squared over here, right? So that's 15 equals h squared. Okay. So the opposite side over here is the negative square root of 15. Notice I threw the negative in there, right? Okay, because 15 is h squared, which means I'm going to take the square root of both sides. But notice I'm in quadrant 4, and that's important, right? My y value, my opposite side, is going to be a negative when it's on that grid. Okay? So now, the question of this whole thing, that we needed that information to answer the questions, but here's the actual question. They want you to find the sine of u plus w. These are two different angles, and if I add them, I get another angle. Okay, so that's what we're doing here. I'm finding the sine of whatever this other angle is when I put these two together. I don't know what u is, I don't know what w is, I don't care. I also am not going to know what u plus w is. Okay, that's not the goal. I just want the trig ratios of u plus w. This could just as easily have been u minus w or w minus u or so on and so on. Okay? Regardless, here we go. The sine of u plus w is going to be equal to, now I'm using the sine of a plus b up there, so I need the sine of u, right, cosine of w, plus cosine of u, sine of w, right? And what is that going to be equal to here? Well, the sine of u is going to be 5 over 13, right? So now you see why I had to set up and look for the other ratios here. The cosine of w is already given to us, that's 7/8. Plus, the cosine of u is negative 12 over 13. And the sine of w is negative square root of 15 over 8. Okay, so then I will consolidate and simplify here. This is going to be equal to, I've got 35, double negative, so it'll be plus 35 plus 12 square root of 15 divided by, and then I've got 13 times 8, you see, it'll be a common denominator already, so that's 104. Okay, so then this is one of my answers here. Remember, the idea is to get the exact form of these ratios, because yeah, I could have just plugged this in the calculator and got the decimal angle for u, and then I could have done the same thing for w, and then I could have added them, and I could have punched up sine. You could do all that in the calculator, but you're going to get a decimal answer, and that's not the goal here. The goal is to have that exact form. Okay, next, the cosine of u plus w. It's a very similar idea, right? I'm using the cosine formula this time, cosine u, cosine w minus sine u, sine w, from up there, right? And this is the same values, I'm just putting them in a different order here now, right? Cosine of u is the negative 12 over 13. Cosine of w is 7/8. Minus sine of u, 5/13. Sine of w, negative square root of 15/8. Okay? So then let's see, what, again, my denominator is going to be the 104. My numerator this time, though, is going to be negative 84. Double negative here, so plus 5 square root of 15. Okay? So real quick, there's actually more that we can determine here than just this. Now that we've gotten the sine and the cosine of this angle. Now remember, the angle I'm talking about is u plus w. That's one angle, u plus w. Now whatever that angle is, I have its sine and cosine now. Well, that means I could probably find any other angle, any other ratio of that same angle, right? From sine and cosine, I could do sine over cosine would give me tangent. I could do the reciprocal of those two and I get secant and cosecant, and then do the reciprocal of the one I just talked about, tangent, to get cotangent. Okay? So I need these formulas sometimes to do some of the first few of them, but now whatever u plus w is, I have the ability to get all of his trig ratios. On top of that, I can accurately tell you which quadrant the angle u plus w is, even though I don't know what the actual measurement is, right? Think of this. The sine is a positive, because look, everything here is positive. So whatever this ratio is, it's a positive ratio. Okay? So that means u plus w is either in quadrants 1 or 2, right? That's where sine is positive. And let's put the nail in the coffin. Cosine here is negative 84 plus 5 square root of 15 over 104. Well, square root of 15 is really, really close to square root of 16, right, which is 4. 5 times this is going to be a little bit less than 20, but it's positive. And the reason why I'm saying that is because plus a negative 84, this is still going to be a very large negative number in the numerator, which makes this whole thing negative. Since the cosine is negative and the sine is positive, I can tell you for sure that whatever u plus w is, whatever that angle is after you add u and w, it's somewhere in quadrant 2. Okay? So if I were to take this angle and put it on top of w, it would rotate into quadrant 2. Okay? And then very easily we could get the tangent of it, right? I can easily say that tangent of u plus w without doing the formula is just that one divided by that one. So that's 35 plus 12 square root of 15 over negative 84 plus 5 square root of 15. Right? Because the 104s, when you divide, you'd flip and multiply. The 104s would eliminate. Okay? So it'd be very easy to find the rest of the trig ratios from those. And I also know that, as I said, u plus w exists somewhere in quadrant 2. It would go past a full rotation, because w would get this far, and then I would add u, and it would land me in quadrant 2. Okay, so these are the types of things, plus the last scene, okay, that we do with these particular identities. So this next set of identities comes straight off of those sum and difference identities. These are called the double angle identities, and they basically have the same purpose, just a different situation. These are the situation when you have two angles that are added together, let's say, but they're the same angle. So if you go back to those identities that we were just looking at, and instead of doing sine of a plus b, for instance, do sine of a plus a. A plus a is 2a, and you'll notice that the formula would reduce to 2 sine a times cosine a. Okay? Same thing. Cosine of a plus a, cosine of 2a, gives us cosine squared a minus sine squared a, straight off of the sum formula for cosine. Okay? But with some help of the Pythagorean identities that we have, I'm able to manipulate this particular one into two other forms. So we actually have 3 different forms of the cosine of 2a, and you can actually use whichever ones you want. They are 100% equivalent. It just depends on your situation as to what information you have at that time. Okay? So you can literally use any one of these 3 for the cosine of twice an angle. Okay? It doesn't matter which one you use. Personal choice depending on how much work you may see one causing versus another. Okay, and then of course tangent of a plus a, same thing. You get 2 tangent a over 1 minus tangent squared of a. Okay, so like I said, the same idea here with these. I'm just going to run through a few examples using the same ideas. We use them to simplify some angles themselves, if I just want to know that. I use them to simplify either identities or expressions that have things that don't mix well together sometimes. And we also will have the analysis of angles that we don't know, but we do know their trig ratios. Okay, so for sine of 240, if I'm going to use a double angle identity, if I'm told find this value, but you must use a double angle identity, okay? The first thing you want to do is I want to write this as a double of some angle so that it fits this format here. So that's going to be the sine of 2 times 120 degrees. Okay, so that's what it means to be in a double angle situation. I'm going to be taking it as the double of some angle. So 120 is my angle in question. Now, that's going to be 2 sine of 120 degrees cosine of 120 degrees. Well, don't forget 120 degrees is a second quadrant angle with a reference angle of 60. Right? 120 degrees has a reference angle of 60 in the second quadrant. Okay, so I'll be using all of the numbers from the 60-degree angle and then the appropriate SIGN for quadrant 2. So 2 times sine of 60 is square root of 3 over 2. And cosine of 60 is 1/2, but the cosine of 120 would be negative 1/2 because it's in quadrant 2 and cosine is negative there. Well, 2 times negative 1/2 is negative 1, and then times that. So I get negative square root of 3 over 2 for my sine of 240 degrees. Which you could also get by just actually graphing out 240 degrees and noticing it's a 60-degree reference angle in quadrant 3. So therefore, sine should be negative in quadrant 3, and the sine of 60 is also square root of 3 over 2. Okay? But you get the point, right? This is the idea of rewriting something as a double of another angle. And then I can use this identity if I need to. Okay, so right here, I have a cosine of 2 times the inverse cosine of x. And boy, wouldn't we just love to be able to just say, oh, cosine, inverse cosine, and wipe out, and I just get 2x, right? No, it does not work that way. Okay? However, since I'm doing something with an inverse cosine, I would probably want to choose the second level here, the second version of this cosine of 2a. Okay, so notice that is exactly what I'm doing here, though. I'm doing a cosine of 2a, where a is the angle that I get if I say that my cosine is x. So this would have to be x along the axis here. This would have to be 1 up here. And this would be the square root of 1 minus x squared on the opposite side over there. Okay? So the cosine of 2a, like I said, I have several choices here. But the real obvious choice is going to have to be this one. 2 cosine squared a minus 1. So that would be 2 cosine squared of the arc cosine of x. Okay? Minus 1. This is the format right here that I'm using. Angle A comes from this arc cosine right here. This is angle A. Okay? So if it indeed is the setup like this, it's simply just going to give me x squared here. The cosine of this literally is x over 1. It's x. Okay? So the cosine of this, remember the squared is shorthand. It's actually this whole thing squared is what that means. Okay? So I'm literally getting x here. So I'm getting 2x squared minus 1. Okay? Here's another way you can look at it. I'll show you they actually get the same thing. If I were to use the cosine of 2a here, but a different format, if I were to use the 1 minus 2 sine squared of a, right, which would be the arc cosine of x, like this, then literally all I'm doing right here, this is still angle A in between here. So the sine of A, quantity squared. The sine of A is just opposite over hypotenuse. It's this thing, right? So I would have 1 minus 2 times square root of 1 minus x squared, squared, like so. But squared and square root just go away, right? Leaves me with 1 minus 2 times 1 minus x squared, like that. Negative 2 times negative x squared, and negative 2 times 1. I have 1 minus 2 plus 2x squared, which lands me right back to this same answer. Okay, so notice it didn't matter which one of those two formulas I use, and literally I could have used any of the three. Okay, you're going to get the same answer. So this thing simplified is 2x squared minus 1. All right, so next, given the sine of some angle u is 2/5, and u is in quadrant 1, find the tangent of 2 times u, the double of u, and also find the tangent of 3u, the triple of u. Well, wait a minute, I don't have a formula for that one. Hang on, I'll show you how you can get to that one. Okay, so let's start here. The tangent of 2 times u. That's this formula here, which means I need the tangent of u for that formula. I don't have the tangent of u, I've got the sine of u. Well, I can easily get the tangent of u, right? By coming over and drawing out what u is. Sine is 2/5, so opposite is 2, hypotenuse is 5. And that means that my adjacent side over here, okay, let's call it x, 5 squared is going to be equal to 2 squared plus x squared. So that's 25 is equal to 4 plus x squared. 21 is equal to x squared. So then this bottom side right here is going to be the square root of 21, positive, because it's going in the quadrant 1 direction there. Okay, so I can see now that the tangent of u is going to be equal to 2 over the square root of 21, right? Opposite over adjacent there. 2 square root of 21 over 21. I'll use either one of those, okay? I'll use either one depending on the situation that I'm in. Okay, so let's write this one down. So tangent of 2u is going to be 2 times the tangent of u, which is this. I'll go ahead and use this one, 2 square root of 21 over 21, over 1 minus the tangent squared of u. Okay, now watch this. I'm going to use the 2 over square root of 21 here, like this. Okay, what I'm doing is I'm saving myself a little bit of multiplication here. Notice these two are equivalent, but because this one had a square on it, it's going to get rid of that radical in my denominator there anyway. And that's going to save me a moment. If you don't do that, it's okay. You can use the same representation. Not 2. This is going to be now 4 times the square root of 21 over 21 divided by 1 minus 4 over 21. Right? See, it was easy to square that one and not have a more complicated fraction. From this point, what I'm going to do is multiply by 21 in all 3 places. And that's going to give me 4 square root of 21 over 21 minus 4 here. Okay, so 21 minus 4 is just 17. So I have 4 square root of 21 over 17. And there's my tangent of whatever 2 times u is. Okay? Now the tangent of 3 times u. What I can do for this one is just say this is the tangent of u plus 2u, like this. And then I'll go back to the previous set of identities, right? And do the tangent of a plus b. That's going to give me the tangent of u plus the tangent of 2u divided by 1 minus those 2 multiplied. Well, I've already got the tangent of u and I've got the tangent of 2u, right? I've got both of them. So let's see what happens. Right here, I'm going to get 2 square root of 21 over 21 plus 4 square root of 21 over 17 divided by 1 minus those 2 multiplied. 2 square root of 21 over 21, 4 square root of 21 over 17. Okay? Now, the common denominator for everything is going to be 21 times 17. And notice, if I multiply that in all locations, right? If I multiply by 21 times 17, the 21s will eliminate here. 21 times 17. The 17s will eliminate here. And then when I multiply them here, 21 times 17, they'll both eliminate here. And then I'll just have to do 21 times 17 for this one here. Okay? So then, what I have is 34 square root of 21 plus 84 square root of 21 over 21 times 17. Let's see, that's going to be 210, right? Plus 147. So 210 and 147 is 357. 357 minus, now right here, all I'm getting is 2 times 4, which is going to be 8, times 21, right? Because square root of 21 times square root of 21 is going to give me 21. Okay? So then, I've got 34 square root of 21 plus 84 square root of 21. So that's going to give me 118 square root of 21. Okay. And then in the denominator here, I've got 357 minus 8 times 21. And let's see, that's going to be 168. So then the subtraction of those is going to be 189. Okay? So then I'll leave it like that. So just because I didn't have a formula for that one directly doesn't mean I couldn't use a mixture of some of the other formulas that I've been using already. Okay? And the idea is the same. It's not about finding the decimal. It's about having the exact version of the answer in a closed form of simple operations. Okay? Using just these double angle identities. Okay? Now, real quick, for the next scene, the next set of identities, I want you to remember these two identities right here. Cosine of 2a is equal to 2 cosine squared a minus 1, and cosine of 2a is equal to 1 minus 2 sine squared of a. Okay, the next set of identities come directly off of these two here. Now two categories that are actually related to each other that come off of those two formulas that I just told you to focus on. If you take those two double angle cosine formulas that I was pointing at before, and you just rearrange them by solving for the squared trigonometric term in each, then I can rewrite sine squared of some angle as 1/2 of the quantity 1 minus cosine 2a, and cosine squared as 1/2 1 plus cosine 2a. And these are called the power reduction identities because that's exactly what they do. They take something with a higher power, in this case 2, and bring it down to some other trig with without that exponent. Okay? In this case, I'm bringing sine over to cosine, and cosine stays as cosine. But that's not really the part that's the worry at the time that these are usually used. These are highly used in calculus for exactly this purpose of they don't want the powers, they don't want the exponents. They'd rather take something that's a little bit larger, possibly with more pieces, as long as it doesn't have any of the exponents inside of the terms. Okay? So for these two, for the power reduction identities, for example, I have this one, sine to the 4th of 5x, that we're going to look at. So the thing to notice is that sine to the 4th is the same thing as sine squared squared, right? So in that case, what I have is this. I can rewrite this as sine squared of 5x squared, like so. And then once I do that, I can rewrite sine squared of the 5x this way right here with the 1/2 1 minus cosine of 2a. Okay? So then from there, this piece looks like this. I'll actually get 1/2 1 minus the cosine of, now this is 2a here, right? This is double of the angle. My angle is 5x. So that would mean 10x because it's going to be double 2 times the 5x. And then of course that whole thing is being squared. Okay, so to facilitate that, what I'll do is I'll be squaring the 1/2, and then I'll be foiling this binomial here because this is 1 minus the cosine of 10x times 1 minus the cosine of 10x. And I'm just going to foil it out. So then this is going to be equal to 1/4 times 1 minus 2 cosine of 10x plus cosine squared of 10x. Okay? So from there you see what I've been able to do after foiling this out is I've been able to take something that had originally a 4th power in it, and I've reduced it to something that has more terms, that's the sacrifice, more terms, but it now only has a 2 power in it. So then I can even take it one step further because I can enact the cosine squared identity again, right, on that one. So then what I have is 1/4 times 1 minus 2 cosine of 10x plus 1/2 of 1 plus cosine of the double of that. So this is going to be 20x, like this. And so from here, it's just a matter of combining all of the things that are alike now and just, multiplying everything out. So what I'm going to do is I'm going to distribute this 1/4 in after I've combined everything here, right? I am going to distribute this 1/2 here. So let's see. What I have is 1/4 then times, I'm going to have 1 plus a half. 1 plus a half. So that's 3 halves. Then I've still got the minus 2 cosine of 10x. And now I'm going to have 1/2 cosine 20x. Like so. Okay, so final step, I'll go ahead and distribute the 1/4. This is going to become 3/8 minus 1/2 cosine of 10x plus 1/8 cosine of 20x. Okay, so I have the sine to the 4th of 5x. Sure, it's simple, it's one term, and you know it's very simplified looking, but maybe the exponent is really giving me issues with whatever operation I'm doing. So to get rid of that power, I'm using power reduction identities. And notice the thing that I eventually turn it into is something that has the cosine, that still has the trig, but no exponents. And that's the goal of using a power reduction identity. So from the power reduction identities, I can go another step further. I can then turn these a's and 2a's around so that they take the place of a 1/2 and a whole, right? Because technically 1 is half of 2, and they just rearrange the names around, really. And then I get rid of the squares by square rooting. So then the half angle identities come from these directly. Basically, this is just solving in these. The sine of the half of an angle is given as the square root here, and notice the plus or minus. Same thing with the cosine of the half, it has the plus or minus. Some knowledge about the angle itself is necessary in order to decide whether your answer should be positive or negative, because that's going to depend on the quadrant of the angle that you're dealing with. Okay. Now, of course, there's a tangent half angle one here, and that comes from just doing the sine over the cosine. Hence, you can see that's those two patterns. But the nice thing about this one is through multiplying conjugates, I'm able to simplify this into something that actually doesn't even have the square root in them. And these two are actually equivalent to this top one. Again, this is like a trio thing where this one identity, tangent of the half of some angle, actually has 3 different ways of being calculated. And typically we don't even use this top one. We use one of these 2 bottom ones. Personally, I like the one in the middle the most. Okay, so for example, if I want to compute the tangent of 75 but using a half angle identity, okay, maybe you were told you got to use a half angle, or maybe it's just the first thing that came to mind. Just as before, you want to rewrite the thing inside of here, and the argument here, as whatever structure is going along with these formulas. So in this case, I would want to rewrite this as the tangent of 1/2 times 150 degrees. So 75 degrees is not a memorized angle. It's not one of the ones that we easily can get to. I could do one of the sum identities earlier, but this one's actually going to be faster. Tangent of 1/2 of 150 degrees. So then what this becomes is, right here I'm going to use this, the tangent of 1/2 of an angle. I do 1 minus the cosine of that angle over the sine of the angle that's in the 1/2. And that's why I rewrite this, so that I can actually see what my A is here. Here it's going to be 150. Okay, so then this becomes 1 minus the cosine of 150 degrees divided by the sine of 150 degrees. Okay, and don't forget 150 degrees is the angle in quadrant 2, right? That has a reference angle over here of 30 degrees. So therefore, in that second quadrant, I will have a cosine that is negative and a sine that is positive, and I'm going to use the numbers from the 30-degree angle. The cosine of 30 degrees is square root of 3 over 2. The sine of 30 degrees is 1/2. So the cosine of 150 is negative square root of 3 over 2. And the sine is also positive 1/2. If I multiply by 2 here, here, and here, right? That's our little maneuver for simplifying these kinds of compound fractions. If I multiply by 2 here, here, and here, that will get rid of all of my small 2 denominators. And I will see that I'm getting 2 plus, because of the double negative, square root of 3. And then over 1, right? So it's just itself. This is the value right here. Okay? So the tangent of 75 degrees is 2 plus the square root of 3. And that's using the half angle identity. Just like the other sets of identities that we saw, there's also the application where there's an angle that I don't know, but I do know one of his ratios. And as long as I have some other information about that angle, then I can answer some sort of question using these identities here. So I have theta is some angle such that his cotangent is -3, and theta is something in radians between pi over 2 and pi. Well, don't forget, being between pi over 2 and pi, this means that theta is in quadrant 2. Okay? So this is really just two different ways of saying the same thing. However, I do need to actually write it this way for this particular problem, and that's because I need to do some solving. I need to know some information about the half of theta, and that's because when I'm answering this question, I need to be able to choose plus or minus. So I need to know which quadrant-ish, if I can. And actually, we can very quickly here. Notice that if theta is in between pi over 2 and pi, if I were to multiply by 1/2 here, here, and here, just basically multiply by 1/2 everywhere there, and I picked 1/2 so that I'd get 1/2 of theta in the middle, that's why. Then what I get is pi over 4 less than or equal to 1/2 of theta less than or equal to pi over 2. Okay? So just multiplying the 1/2 everywhere there shows me that the half of theta is somewhere between pi over 4 and pi over 2. In other words, it's somewhere between 45 degrees and 90 degrees. Therefore, if it's between 45 and 90, I know that 1/2 of theta must exist in quadrant 1. Right? Theta itself is in quadrant 2, but multiplying out the 1/2 there shows me that the 1/2 theta, this angle that I'm trying to take the cosine of, exists in quadrant 1. Therefore, when I'm doing this calculation, I'm going to pick the positive, not the negative, because it's in quadrant 1. And it will be the square root of 1/2 times 1 plus the cosine of theta, right? Because it's this angle here, and I'm plugging it into this formula here. So all I need to do now is figure out what the cosine of theta is represented with, and we can do that by drawing out the angle again, right? So cotangent of theta. Now remember, theta is in quadrant 2, right? So I'm drawing out this angle, okay? This piece of information was just to answer positive or negative over here. What I'm actually drawing now is theta itself, not 1/2 theta. So if I draw theta, we know it to be somewhere in quadrant 2 there, okay? And we were told that its cotangent is -3. Now remember, cotangent is adjacent over opposite. So that means this would have to be -3 and this would have to be 1. So then, using Pythagorean theorem, I have 1 squared plus 3 squared is 1 plus 9 is 10. So this has to be the square root of 10 for the hypotenuse. And therefore, I can figure out the cosine of theta post haste here most quickly. So then this is going to be equal to 1/2 times 1 minus, right, because cosine here is going to be adjacent over hypotenuse, minus 3 over the square root of 10. Which, of course, I can go ahead and simplify out. This is going to be 3 square root of 10 over 10. Right? That's how I'm going to do my cosine there, by rationalizing it. Right here, though, also what I can do is I can write this as 10 over 10. Right here, the 1. So square root of 1/2. And then I've got 10 over 10 minus 3 square root of 10 over 10. Okay? Which is then going to show me that I have 1/2 times 10 minus 3 square root of 10 all over 10. And then what I can do with this is I can just multiply the 2 and the 10. Okay? So then it's telling me this right here, that I've got square root of 1 over 20 times 10 minus 3 square root of 10. And really, it doesn't need to go much further than that. It is a nested radical, right? I have the square root of 10 inside of the other square root. But the goal is achieved. I wanted a exact version of the cosine of this angle. I do have that. You can manipulate it and do other things with it, like trying to write the 20 as a denominator and maybe rationalizing it and doing all sorts of things like that. It just depends on which way you need to use the data in your situation. But this is a good average place to sort of leave it. It is simplified. It is concise. It is just a few symbols there. Okay? So that's the half angle identities. The last set of identities I want to talk about here are ones that are sort of pushed off to the side a lot in a lot of trig classes. I want to mention them because these do come up in later math courses. You do need to know these exist, especially if you're going to be taking Calculus 1 and 2. Okay, so the product to sum and the sum to product identities are ones that come straight off of the very first identities that we talked about in this lecture, the sum and difference identities. If you take two of the sum and difference identities and either add them or subtract them together, or find some of their results and combine them together and basically solve them like a system, in a way, then what you can do is you can create these sort of identities where it takes the multiplication of two things and turns it into the addition of two trig functions where the angles are combined. Or you can find some combinations where if you're adding two trig functions or subtracting two trig functions directly, then you can turn it into a multiplication where the angles are sort of combined like that as well. Okay? And it just depends on your situation. There are going to be situations where you have to take a product and split it up so that you can look at the pieces individually. And then there's other times where you have two separate trig functions and you want to merge them. And it really is situation specific. In calculus, there are integrals that cannot be done when things are in the particular multiplied form. There are what we call integrals, which are operations that work good when the arguments are the same or when it's just one of the trig functions or something like that. But notice in this kind of situation where the trig functions are different and the angles inside are slightly different, one is 9x, one is 11x, the things in our calculus doesn't work quite as nicely. So it would be better if they were split apart. Okay? So in a situation like this, I would come over to my little product to sum identity and say, okay, what can I set up here so that I can turn it into two things that are split up? And that's exactly what we're going to do here. I'm going to take this and I'm going to rewrite it. The first thing I'm going to notice is my identity has the sine of A and the cosine of B. What that means is, notice where the A minus B is right here. You want to make sure that you have that subtraction in the correct order. So A is whatever the thing is with the sine, and B is whatever comes with the cosine for this formula here, specifically. Okay, so for this piece right here, cosine of 9x times sine of 11x, I'm going to say that that's equal to 1/2 times the sine of A plus B, which is going to be 9x plus 11x, plus the sine of A minus B, which in our case is going to be 11x minus 9x, like so. Right? Because that was the way these were ordered. Our B is technically the 9x. Our A is technically the 11x. Okay, so then what I have here is that this is 1/2 times sine of 18x. Oh, no, not 18. I forgot how to add for some reason. 20x. And then plus sine of 2x. And I know what you're thinking. Well, those are still different angles and stuff like that. Sure, one's 20x and one's 2x, but the major difference here is not the angles. It's that I still have my two trig functions and they're no longer multiplied. Okay? For a lot of our applications in calculus, things that are added are easier to split up and work separately. It just depends on the needs of the particular application. In that case, I needed to go from a product to a sum. Okay, next, what if I need to do a calculation where I don't know either of the two angles, but maybe another combination of them would work? Okay, so I have this particular subtraction here. Maybe it would work better if I were able to combine these angles some. So I come over here and I look at my sum to product IDs, and I don't see one that has a sine minus a cosine. That's okay. I can still switch over to something that's a sine minus a sine because I remembered, oh yeah, I have a cofunction identity. Remember, the cosine of some angle is also equal to the sine of its complement, 90 minus the angle, right? So in this case right here, I can convert this cosine into a sine, and all I would need to do is 90 minus the 75. So my first step would be that. In this case, I would have sine of 165 degrees minus the sine of 15 degrees. Cosine of 75 and sine of 15 are exactly equal to each other. And now I've got a sine of A minus sine of B set up. My A is 165, my B is 15. So this is now going to be equal to 2 times the sine of A minus B over 2. So 165 minus 15 over 2 times the cosine of A plus B over 2. So 165 plus 15 over 2, like so. Okay? So then 165 minus the 15, what I get from that is 150, right, divided by 2. So I have 2 sine of 75 degrees. And then over here for my cosine, I have 165 plus 15, which is 180, divided by 2. I have the cosine of 90 degrees, right? Well, the sine of 75 I can figure out through one of my other formulas from earlier in this section, right? That wouldn't be too hard of a problem. But here's the other cool piece of this one. The cosine of 90, right here, cosine of 90 is 0. And it's multiplied this time now instead of added or subtracted, right? So then what we're actually getting here is that the final result is 0, right? The sine of 165 minus the cosine of 75. Let's even check it. Look, I'll put it in degrees. Sine 165 minus cosine 75. 0. In a roundabout way, what that also is a way of proving two things are equal if their subtraction is equal to 0. Okay, so that's another bonus of that particular calculation. Okay, now one more application here of these is if I'm trying to solve an equation. Let's say I want to know where this trig function is equal to this other one. Maybe I'm looking at their graphs and I want to know where they intersect. There are many ways of doing this, as you're going to see in the next couple of sections. We have many ways of solving these kinds of things, but some of them can get kind of messy. And if I notice I have something as simple as just two cosines, let's say like this, their angles are different slightly, but they're still just the two cosines and that's it. Well, maybe there's a way I can interact those two like this. And if I had it equal to 0 and a multiplication, I would be able to split up and solve much more easily. So in other words, I would subtract here first and make it cosine of 5x minus the cosine of 2x is equal to 0. And now that it's equal to 0, if this were a multiplication, I would be able to split it up into much simpler equations. So that's what I'm going to do. I'm going to convert it using this cosine minus cosine sum to product format. So right here, that means that this is going to be 2 times the sine of 5x plus 2x over 2 times the sine of 5x minus 2x over 2, like so, is equal to 0. So I have 2 times the sine of 7 over 2x times the sine of 3 over 2x. And here, since this is multiplied and equal to 0, I can simply split it and say, all right, now figure out where sine of 7/2 x is equal to 0, or where sine of 3 over 2x is equal to 0. And each of those would be a much simpler equation to solve rather than trying to figure out where two cosines are equal or trying to find some other way to find common terms and merge them here. Each of these are plain and simple, one trig, one number, and equal to 0 even, much easier to solve than that one. Okay, so sometimes it's about the structure of splitting things apart with multiplication. Other times it's more important to have things to split apart as addition. This kind of switch around is very important for trig because there's really just no other way to do it. Kind of like with your log rules, how we have ways of taking a logarithm of a product and turning it into the sum of two logarithms, right? There's always those little rules of these, especially transcendental type functions, that you just need to know. So I hope this lecture has shown you a good insight of the beginning of all of the thousands of trigonometric identities that are out there. And the reason they're out there is because someone had a use for them at one point in time. I hope this gave you a good idea of how to go about using these trig identities to help in many, many different situations.